Now let's try it again with a hexagon. Now a hexagon is a little different because like in a hexagon and an equilateral triangle, when you divide the triangles, either the hexagon or the triangle up into smaller triangles, you get special right triangles. And that's just because of the type of angles we're working with. So if we divided this hexagon into 6 triangles, these angles would each be 60 degrees because there are 6 of them, and they can make a full circle. And each of these side lengths are 6, so that's going to be the base of each triangle. So if I go to find the area, I'm going to split that in half, and I create a side that's 3 and 3. And each of these angles are going to be 30 because 60 got split in half. So this side would be 60, which makes this height right here 3 root 3. So now, if I'm finding the area of one of those triangles, I'm going to do the base, which was 6, make sure you use the whole base, times the height, which is 3 root 3, and then divide by 2. So we get 9 root 3 as the area of one of these triangles. Well, that's 1/6 of the whole picture, so you got to multiply it by 6. And when dealing with special right triangles, you should leave it like that as a radical, an exact answer. And we get 54 root 3 square units as the area of this hexagon. So find the base, find the height, use trig to do that, multiply it by a number of triangles. So there is a formula that goes with the area of a regular polygon. I wouldn't try to blindly memorize it and hope you could plug stuff in. I think it helps to understand how it works. And a lot of times not all of these things will be given, so you have to know how to find it. That's most of the battle, using trig to find either the apothem or the side length. So one way to look at it is n, and that's the number of sides, times the area of each triangle. So the formula 1/2 NAS, which is a variation of this, works because n is the number of sides and 1/2 NAS is the area of each triangle. Because S is the length of each side, so if you divide this into triangles, S is the base, and the height is A, the apothem. That's the distance, perpendicular distance from the center to a side. So doing 1/2 S times A is the area of this triangle times the number of triangles. And another formula that's used is 1/2 A times the perimeter. So if you know the perimeter, or you could find it by doing the length of each side times the number of sides, since n times S is equal to the perimeter, you can also do 1/2 the apothem times the perimeter, and you'll get the same answer. So another way to think about it. And if you don't have A, but you know the perimeter, you could divide the perimeter by the number of sides to find the length of each side, then use trig to find A, which is the height of each triangle, and stands for apothem. Alright, last one is we're going to find the area of a triangle. And it's kind of funky because we're going to break a triangle up into smaller triangles, and that's okay. It's just it's a good exercise to help us practice finding the area of bigger types of regular polygons. But this is an equilateral triangle, and it's still a regular, so it doesn't say, but we should assume it's regular. A regular triangle is a regular polygon. And this right here is the radius, because it's going from the center of the triangle to a vertex. So if I were to inscribe that triangle in a circle, that would be the radius of the circle. So what I'm going to do is draw 2 more radii, and now I divided this triangle into 3 triangles. Now, so now it's this is like an isosceles triangle, where I only know 2 sides. But I could actually figure out that these angles here are 120 because they're all equal to each other, because again, side, side, side. We don't know these side lengths yet, but we can assume they're equal because it's a regular triangle. So these base angles are equal. So we divide by 3 and you get 120, which means when we split it in half, each of these angles is going to be 60. So then by default, these angles down here have to be 30. And then it's like we have the hypotenuse of this right triangle here is 7, which would make this height here 3.5 because it's half of 7, and the short leg is always half the hypotenuse, which would make this leg 3.5 root 3, and also this leg 3.5 root 3, which would make the entire side of the triangle 7 root 3, because I'm just adding the two sides together. So now you could do this a couple different ways. One way you could do it would be to find the area of like one of these triangles by doing the base, which would be 7 root 3, times the height, which would be 3.5, and then divide by 2. And then since there's 3 of those triangles, I'm going to multiply it by 3. Now to do that on my calculator, to keep it to keep it exact, I'm going to multiply 7, 3.5, and 3 together, and I get 73.5, and then divide by 2, and I get 36.75, and then I could keep it in terms of radical 3. So yes, I am using a decimal, but it's not rounded. If you wanted an approximated answer, all to a decimal, you could multiply in the root 3, and you get 63.65. That would equal 36.75 root 3 is equal to that. Now the other way you could do it is to just look at this as one big triangle, and then do the length of the base, which would be 7.5 root 3, times the height, which would be 7 plus 3.5, so times 10.5, and then divide it by 2. And when you multiply 7.5 times 10.5 together and divide by 2, we get the same answer as we did here. And sorry, there was a small typo in that explanation right here. That should be a 7, not a 7.5. And then that would give us the same exact answer. So I apologize. And that's because this length right here is 3.5 root 3 plus 3.5 root 3, which would just be 7 root 3, not 7.5. Alright, that's it. Thanks.